Hi, welcome back. Today we're going to take a look at the fundamental theorem of line integrals. So let's go ahead and get kind of started on this a little bit. We're going to review how the fundamental theorem works again, but first we're given a vector field, the following vector field here. And we want to know if this is conservative, and if it is conservative, find the potential function. So to determine if something is conservative, we're going to look at the partial. This is my vector field. That's M, and that's our N, P, Q, depending on your book. To find if a vector field is conservative, we want to make sure that the partial of n, which is with respect to x, but remember this is our second derivative. This is like saying the function of yx is equal to f xy. So remember this that Clairaut's thing. We want to make sure that Clairaut's theorem holds here. So the partial of m is also equal to the partial of m with respect to y. And I can check that real quickly. The partial of n with respect to x is just 1/2 x. The partial of m with respect to y is also 1/2 x. So this is conservative. To get the vector field, to get the potential function, remember we're just going to look at each component independently from each other. So looking at the x's, I am going to integrate m, the 1/2 xy, with respect to x, because I'm checking if the derivative with respect to x, that's what I'm checking here from my original function here. And if I integrate this one, we would get 1/4 x squared y plus some constant with respect to y. Same thing with the y's. We would get this 1/4, x squared dy, and that would give us 1/4 x squared y plus c with respect to x. If you forgot how to do these, we've done these in a previous video. Please look back and you can take a look at those. All right, so to get the actual function, the potential function here, we're going to look at what they have in common, which is that 1/4 x squared y. They both have a constant, so we're just going to add a generic constant there as well. We don't know what it is. Now remember, to get the potential function, you look at what they have in common and anything extra that they have left. So we just leave it like this in this case. All right, so now what we want to do is we want to find the work. We want to find the work done by our vector field up here on the following path, yx and y equals x squared from 0, 0 to 1, 1. So let's redefine work here. So work, you might remember, is the line integral of our vector field times our magnitude of our displacement. Sorry about that. So we can't really integrate this one because you really can't integrate over an entire path. So we simplified it to this. We're going to make it into a parametric. We take the vector field dot our derivative of our path, r prime, and since we make it parametric, it's going to be dt. And that's going to be our rule, where r prime, remember, is the rate of our path. So let's see here. So let's go ahead and cook. So for the first one, we have this y equals x. And if we look at it, it's very simple. We're going from 0, 0 to 1, 1. And we want to find the work done on this path. Remember, we have all these little vector fields coming along over here, everywhere. And we just want to find out what's the net sum of the work on that path right there. So we're going to make it into a parametric. So the first one's easy. So we have y equals x. So if we let x be t, y is t. So our vector field, if we rewrite it, a vector field with respect to t. Now, remember, this is 1/2 xy, so that just becomes 1/2 t squared, because t times t. Then we have this 1/4 x squared, and that becomes 1/4 t squared. Our prime, remember, our that's this right here. So we can say r is tt. So r prime is just going to be 1, 1. So I'm going to go ahead and evaluate this integral here. I'm going to set it up. So our vector field, which is this 1/2 t squared, comma 1/4 t squared, dot that with this 1, 1 dt. Whoops, got the 1 there. I do got to find my change in time, and that's not too hard to do, to find the change in time. If I look at here, if I look at the x's, remember, we're going from 0, 0 to 1, 1. So x, which is t, starts at 0, and x equals t ends at 1. So we're going from 0 to 1. Evaluating this is going to become the integral 1/2 t squared plus 1/4 t squared. And if we integrate that now, we would get 1/6 t cubed plus, what's that, 1/12 t cubed dt. Oh, sorry, we just integrated that, don't need that anymore. Going from 0 to 1, and that's going to give us 1/6 plus 1/12. And we can simplify this as well. That just becomes, what's that? That's 2 over 12, which is 3/12, which is just 1/4. And there is our work. So let's see what happens if we go take the same vector field and apply it to our path, this y equals x squared right here. Same thing, we're looking at y equals x squared from 0, 0 to 1, 1. We're obviously traveling a little bit further, but let's see how much work will be done. So same thing, y is equal to x squared, so I can say x equals t, y is going to be t squared. I will need their derivatives again. Because remember, this is my path, t comma t squared. All right, so to get the path on this one right here, so let's go. T is also going to go from 0 to 1, because remember, easy check. If I let x be t, x starts at 0 and x ends at 1. So we're going from 0 to 1 again. So let's see here. Our vector field. All right, let's go and let's do this. Remember, it's up here. It's 1/2 x times y. So that's just going to become 1/2 t cubed. Same thing over here. Our y's are this 1/4 x squared, which just becomes 1/4 t squared. And r prime, which is just going to be 1 comma 2t. Dot them together. Let's go and set this up. It's going to be from 0 to 1. 1/2 t cubed, 1/4 t squared. Dot that with 1 comma 2t dt. And if you integrate this, you are going to get 1/4. We're going to shave this we're going to move this kind of long here. All right, so you are going to get this 1/4 again. But what I want you to notice is we do get 1/4, but notice we get the same answer regardless of the path. And that's really what the whole point of this lesson is today. If we know a vector field is conservative, it was what we call path independent. And that's what they're saying here. What can we conclude? The path doesn't matter if the vector field is conservative. If our vector field is conservative. So we don't worry about the path right there. In other words, we call this path independent. And so let's take a look at what that kind of means for us right here. So what does that mean for us right here? If a vector field is conservative, we can treat it like we did last year in calculus. You might recall from Calc 1. If a vector field is conservative, I can take an antiderivative. We have the fundamental theorem of calculus. If I know the derivative, I can find the original function. That's going to become f of x, and we can evaluate that from a to b. And that's going to give us f of b minus f of a. Well, the same thing is true for line integrals. In Cal 1, we found area under a curve. This year in multi, we are integrating over a path itself. So what we can say is if we know a vector field is conservative, we can just use the fundamental theorem of calculus. Take the antiderivative, get the potential function, and then just apply our points. So in other words, like I said, just like last year, we can think of our work integral as the following. Take a look here. Here's our initial xy point. Here's our ending xy point. So if we integrate it, we would just get some little function. We would get our function f of xy, and we can evaluate that from x1, y1 to x2, y2, and that's just going to give us f of x2, y2 minus f of x1, y1 right here. So let's apply this to our previous problem from above. We wanted to solve our little function right here. So let me go ahead and copy that down here. Let me fancy here with my pen here. Copy. And let's see here. Come here. Paste it. Oop, it did not. Okay, it did not copy it. So we wanted to solve this right here. This vector field that we were given, 1/2 xy, 1/4 x squared. So what does the rule say to do? Well, in order to evaluate that vector field, it's like saying we're going to go from 0, 0 to 1, 1. And if we do this FDR, that's going to give me my potential function. Well, what was our potential function that we saw earlier? This 1/4 x squared y. So we get this 1/4 x squared y, evaluate that from 0, 0 to 1, 1. And that's going to give us 1/4 minus 0, which is 1/4. And that took us a lot less longer to do. So let's apply it. Example number 1 here. Evaluate the following line integrals of a vector field with the given potential function. So again, we are given a vector. We are given a vector field and this path. Now notice we don't know the equation of this path. So what I want to do is I want to see if this is conservative, because if it's conservative, then I really don't worry about the path. So there's m and there's n. So the partial of m with respect to y, that is just going to become 2x. And the partial of n with respect to x, that's also 2x. So this is conservative. So my rule, so this is conservative. And because it's conservative, I'm going to use what we call the fundamental theorem of line integrals. So get the potential function with x's, same thing we did before. Take this 2xy with respect to x, and that's just going to become x squared y plus some constant with respect to y. The same thing with the y, and that's going to become this x squared minus y dy, and that's just going to become x squared y plus y squared plus some constant with respect to x. So our potential function now is going to be the following. Take what they have in common, this x squared y, and what they don't have in common, the extra, this y squared, plus some constant. Using the fundamental theorem of line integrals, now rather than making this into a parametric, which could be ugly, I could just use my fundamental theorem because it is conservative. It just says, take your potential function that you just found, that's my integral. From BC calculus, that's just my antiderivative. I just found my antiderivative. We talked about potential functions earlier. This is just my antiderivative. I'm just going to evaluate it from my starting point, which is this negative 1, 4, to my ending point, which is 1, 2. Evaluating that using the fundamental theorem, that's just going to become 1 times 2 plus 4. Plug in the negative 1. That's just 1 times 4 plus 16. And there is your evaluation right there. All right, hope you enjoyed this video. We're going to do a couple more in just a few moments. Please join us in part 2.